Believe me, Jim, engine temperature control and cooling system maintenance become increasingly important every year.
Why do you say that, Bob?
Well, look at it this way. An internal combustion engine's job is to convert heat energy into mechanical energy. And if you want to take more power out of an engine, you have to put more heat energy in. Now, when we demand more performance from our engines and increase the load on the engine by pulling trailers and operating high-load accessories like air conditioning, we are simply asking for more power. That, in turn, means more heat. One of the additional heat loads placed on the cooling system comes from the automatic transmission. It isn't unusual for the automatic transmission fluid in the converter to get up to 300 degrees. The temperature would go higher than that if it weren't for the oil cooler. The coolant in the lower tank of the radiator absorbs enough heat from the transmission fluid flowing through the oil cooler to prevent oil deterioration from excess heat. This just adds to the heat load placed on the cooling system.
Air-conditioned cars present another heat problem for the engine cooling system. The engine has the extra job of driving the compressor, but that adds only slightly to the heat load. The big air conditioning heat load on the cooling system comes from the condenser. Since it is located directly in front of the radiator and sometimes operates at temperatures above 250 degrees, it pours a lot of heat through the radiator cooling fins. It's a good idea to follow the recommendations in the owner's manual and shift into neutral when stopped by a traffic jam in hot weather. This takes the torque converter load off the engine, lets the idle speed increase so the fan can pull more air through the radiator to increase cooling. And even engine design adds to the heat problem.
How so, Tech?
Designing engines to meet exhaust emission standards actually adds to the heat load on the cooling system, particularly at idle where the emission problem is greatest. Maybe you better explain that, Bob.
Okay, Tech. Complete combustion of a lean mixture is required to reduce the exhaust emission to an acceptable level. However, a lean mixture doesn't always burn completely at idle speed. Here's why. At closed throttle, a relatively small amount of air-fuel mixture is pulled into each cylinder. The fuel particles aren't very close together, and the flame has trouble traveling from one fuel particle to the next. Matter of fact, the fire sometimes goes out before all the fuel is burned. To prevent this, current engines are designed so that the throttle is open a bit more at idle. This allows more of the lean mixture to be drawn into each cylinder. Compressing a greater amount of lean mixture packs the fuel particles closer together, so the flame travels from particle to particle easily to provide complete and clean combustion.
It would seem to me that if you open the throttle enough to clean up combustion, engine idle speed would go sky high.
That's exactly what would happen if we didn't also make some ignition timing changes. Comparatively speaking, the basic ignition timing on current engines is retarded. That means the fuel mixture is ignited later and produces less power from more mixture. This in turn keeps engine idle speed down in spite of the fact that the throttle is open more at idle.
Why is that, Tech?
Because more of the burning takes place in the lower part of the power stroke. Less of the heat energy is converted into power. More heat goes out the exhaust and through the cylinder walls and into the water jacket. As a matter of fact, the entire exhaust port area is subjected to higher temperatures and more heat. This means more heat rejection to both the exhaust system and the cooling system.
Just what is meant by heat rejection?
Only about 1/3 of the heat energy in the fuel produces power. The other 2/3 represents heat that would damage engine parts if we didn't get rid of it. We refer to the job of getting rid of that 2/3 as heat rejection. About 1/3 of the heat energy goes out through the exhaust system. The other 1/3 of the heat energy has to be handled by the cooling system.
Getting rid of the unused and unwanted heat is only part of the engine temperature control story. Quick, uniform warm-up is just about as important as heat removal.
I was just about to get to that part of the cooling system story. Soon after an engine starts, the flame temperature in the combustion chamber may go as high as 4,000 degrees. By comparison, the rest of the engine is still pretty cold, so the cooling system must equalize these temperature differences. The cooling system is designed to pick up more heat from the hot areas, less from the cool areas. This equalizes engine temperature to minimize distortion of engine parts and reduce cold engine wear. During warm-up, the thermostat remains closed and blocks the flow of coolant to the radiator. However, an internal bypass allows the water pump to circulate coolant throughout the engine. This internal recirculation of the coolant promotes fast warm-up. By bringing all parts of the engine up to operating temperature as fast as possible, combustion blow-by is reduced, lubrication is improved, wear is minimized, and better combustion during warm-up is obtained. Some of this year's models are equipped with 190 or 200-degree thermostats. These higher ratings provide higher operating temperatures to improve combustion and reduced exhaust emissions. The old 160 thermostat is gone with the dodo bird.
Key correction, Bob. A 160-degree thermostat is still used on trucks equipped with a thermostatically controlled shutter. That's so the coolant thermostat won't fight with the shutter stat control.
Tell me, Tech, just what does the temperature rating of a thermostat mean?
The temperature rating tells you when the thermostat starts to open. For example, a 190-degree thermostat starts to open at 190 and is wide open about 210 degrees. When testing a thermostat, remember that it should start to open at the rated temperature, plus or minus about 5 degrees, and should be fully open about 20 degrees above rated temperature. And that should bring us to the radiator.
As soon as the thermostat opens, the hot coolant flows out of the engine and through the radiator passages, giving up heat and cooling down as it goes. From the bottom tank of the radiator, the coolant is then pumped through the coolant passages in the engine block and head. The internal flow path is tailored for each engine to minimize temperature variations. Generally, coolant is pumped through the water jacket surrounding the cylinders, up into the cylinder head, and then back to the thermostat housing.
Before we get away from the subject of radiators, how about explaining exactly how this radiator pressure vent cap works?
Gladly, Jim. As you know, liquids boil at a higher temperature when under pressure. So a pressure cap is used to raise the boiling point of the coolant.
Just like a pressure cooker, huh?
Exactly. Pressurizing the cooling system allows the system to run at higher temperatures without boiling off the coolant. Also, a greater temperature difference between the coolant and the outside air speeds up transfer of heat from the coolant to the air. However, excessive pressure on the cooling system could damage the hoses, radiator core, or heater core. If the pressure goes higher than the rating of the cap acts like a safety valve and relieves the excess pressure. The vent you asked about is a second valve, and its purpose is a bit different. When the heat load on the cooling system isn't great enough to require pressurizing, the vent valve drops down and is open. The cooling system operates at atmospheric pressure. This eliminates unnecessary pressure and strain on the radiator, heater, and hoses. Under severe operating conditions, the coolant may reach its boiling point. If this happens, the rush of vapor seats the vent valve, and the entire cooling system is pressurized.
As soon as the temperature of the coolant and the pressure on the system is reduced, the vent valve opens. The system again operates at atmospheric pressure. Be sure and check the vent valve and inspect the cap gasket when you service the cooling system. If that vent valve doesn't open, the system will operate under pressure at all times. If the vent is stuck open or the gasket is damaged, the system won't pressurize. And now if you want to hear what Bob and I have to say about cooling and coolant, you'll have to turn the record. The radiator may be called upon to get rid of as much as 6,000 BTUs per minute. And that's enough to heat most modern homes in cold winter weather. It takes a lot of air movement through the radiator to handle that much heat. At highway speeds, ram airflow through the radiator is great enough to handle most of the cooling job. At low speed, a cooling fan is needed to move enough air to get rid of the heat rejected to the cooling system. Since there's more to fan design than a few blades and a drive pulley, we better talk about fans next.
Okay, Tech. The fan must move enough air at low speed to do the cooling job and yet be reasonably quiet at high engine speed. Several things can be done to improve airflow and fan efficiency. For example, on some models, a fan shroud is used to increase airflow through the radiator. The shroud works something like a wind tunnel and prevents recirculation of the air behind the radiator. Even the seal between the top yoke of the radiator and the hood improves airflow. This seal helps reduce recirculation. Also, it prevents ram air from going over the top of the radiator and therefore improves airflow through the core.
If more cooling is required for heavy-duty operation, such as hauling a trailer with an air-conditioned car, the owner should order the factory-installed trailer towing package. Many heavy-duty cooling systems use a fluid fan drive. This lets us use a higher capacity fan and higher fan speed to deliver more air when it's needed, and yet have less fan noise when the extra airflow isn't needed.
I'm not sure I understand how that works.
A fluid fan drive is simply a fluid coupling. It starts to slip at high engine speed when the torque load on the fan gets up to the point where we don't want the fan to go any faster.
I don't see how limiting the top speed helps low-speed cooling.
A high-capacity fan like this one with 7 blades is used with the fluid fan drive. This type of fan will move a lot more air than a regular duty fan. In addition, a smaller fan pulley or higher fan drive ratio is used to increase fan speed in relation to engine speed. The combination of a high-capacity fan and higher fan speed greatly improves low-speed cooling.
I get it. By limiting the top speed of the fan, the noise level is kept down at highway speeds. This ought to save some horsepower at higher speeds, too, shouldn't it?
It sure does, Jim. And here's something important to remember. When a car is equipped with a smaller pulley, a smaller water pump impeller is usually used. That's because the water pump is driven directly by the pulley and not through the fluid fan drive. When you install a new water pump, be sure and use the correct one. If you install a pump with a large impeller on a car having a cooling system designed for a small pulley and small impeller, the big impeller can build up enough pressure to blow off hoses and cause other damage. And here's something else you should know. 2 different types of fluid fan drives are used on our vehicles. One is a straight fluid coupling. The other one is a temperature-sensitive fluid coupling. And these fluid couplings are made in different sizes and with different peak torque ratings.
You'd better explain that, Bob.
The straight fluid coupling type fan drive simply limits top fan speed. The temperature-sensitive unit also limits top fan speed, but in addition, it lets the fan loaf when the radiator is cold. Here's how it works. This thermostatic coil on the front of the coupling controls the opening and closing of an orifice inside the drive unit. When the coil is cold, the internal orifice is closed, and the fluid coupling simply loafs. When the cooling system thermostat opens and the hot coolant warms the radiator, hot airflow from the radiator warms the thermostatic coil on the front of the coupling. The coil opens the internal orifice at about 165 degrees. Opening the internal orifice pressurizes the fluid coupling, and it drives the fan. The fan speed increases until the coupling reaches its peak torque rating and can't be driven any faster.
This fan drive sometimes plays tricks when it's cold out. The fan may be driven at high speed when the engine is first started and it's very cold. That's because the fluid in the coupling is cold and thick. As soon as the car is driven a short distance, the fluid coupling will operate normally again. And speaking of thick fluid, in production, the peak torque capacity and speed of each coupling is tailored to meet exact cooling system needs by filling it with the correct viscosity hydraulic fluid. If you ever replace one of these units, be sure you get the right size and part number. 2 couplings the same size will not have the same terminal speed if they are filled with different viscosity fluid. And that should just about bring us to the subject of engine coolant. Although water does a good job of picking up and carrying heat, it does have some shortcomings. It promotes rust and corrosion. It boils at relatively low temperature, and it freezes. A solution of ethylene glycol type antifreeze in water makes a good coolant. It has a higher boiling point, retards rust and corrosion, reduces foaming, and it doesn't freeze easily.
But it does wear out, doesn't it?
Ethylene glycol isn't permanent, and it probably should be called 4-season antifreeze. It doesn't exactly wear out, but the inhibitors are used up. The anti-rust and anti-foam inhibitors used in the ethylene glycol are depleted by a combination of engine heat and traces of exhaust gas, which finds its way into the cooling system. This happens even on a tight engine cooling system, which doesn't allow coolant to escape into the combustion chamber.
Why can't you add more inhibitors?
It isn't that simple, Jim. Various inhibitors used aren't compatible. There's a good chance that adding an inhibitor will result in a chemical reaction that will cause cooling problems. As a matter of fact, for foam and corrosion prevention, it's better to use a 40% solution of an approved antifreeze than it is to use water plus inhibitors in warm weather.
Well, just how often should the antifreeze be changed?
We recommend changing antifreeze once a year, preferably in the fall. Even though an owner could stretch the initial change a few extra months, we feel that an annual drain and refill is an inexpensive way to protect the engine and prevent cooling system trouble.
How about flushing?
When the antifreeze is drained, we flush the entire system with clear water. Inspect the thermostat and hoses. Inspect and test the radiator cap. Inspect and adjust belts, and inspect for leaks. Here's how we flush the system. First, we drain the system. To save time, pressure test the radiator cap while the system's draining. As soon as about half the coolant drains, pull the thermostat and inspect it. Next, put a hose into the thermostat opening and let the water run for about 10 minutes, just fast enough to keep the engine jacket full with the drain open.
How about pressure flushing and chemical cleaners?
If you're not careful with pressure flushing, you can pop a heater or radiator core and get into trouble. Pressure flushing and reverse flushing isn't necessary unless there is some unusual cooling system problem. We don't recommend using a chemical cleaner unless the system is very dirty, and that usually means you have a high mileage, neglected, or problem car on your hands. Those jobs are few and far between and require some special service measures.
Speaking of things that are sort of special, our cooling systems have a special anti-collapse coil in the lower radiator hose. This coil keeps water pump suction from collapsing the lower hose. Don't ever install a lower hose without a coil. Here's another warning. I wish we could break people of the habit of overfilling the radiator. The coolant level should be 1.25 inches below the pressure cap seat when the coolant is cool.
What's wrong with overfilling?
Every time you overfill a radiator, you lose some coolant from expansion when the temperature goes up. Constant overfilling introduces more raw water. This dilutes the glycol and the inhibitors in the antifreeze.
It's amazing how much you can learn when you start asking questions, and I sure want to thank you, too, for answering mine.
I'm always glad to help a young fellow who really wants to learn more about his job, Jim. And speaking of learning, don't miss the extra information in this month's reference book. There's a whole section on cooling system service. It covers pressure testing, testing for combustion gas leaks, tracing internal coolant leaks, water pump drive belts, water pumps, and temperature gauges. As a matter of fact, all of you master technicians out there ought to read the reference book from cover to cover and keep it handy for future reference. Today's cooling systems call for a little extra know-how and regular service care.